You ever stop and think about the invisible world that's just humming all around us? I'm talking about the signals bringing GPS to your car, Wi Fi to your laptop, even this content right to your screen. It's not magic. It's all built on a blueprint. And today, we're going to decode that exact academic roadmap that teaches engineers how to build our wireless world.
So let's just start with a really simple question. Think about the things that basically define modern life. What's the one invisible thread that ties them all together?
You guessed it. It's electromagnetism. All of these things run on the very same fundamental principles. These invisible waves carrying information right through the air. You could say these signals are the language of our connected world, and we're about to learn its grammar.
Okay, so to really get this, we're going on a bit of a journey. And our map, well, it's something you probably wouldn't expect. It's a university course syllabus for electromagnetic waves and transmission lines. Yep, this is the exact document that shows how engineers learn to harness these signals one step at a time.
And this quote right here, from the course rationale itself, it just frames the whole thing perfectly. This stuff isn't just abstract theory, you know? The syllabus basically says that if you want to build the tech we rely on every single day, you absolutely have to understand these principles. It is the foundation. So where does an engineer even start? Well, before you can get to waves and signals flying through the air, you have to learn the rules of things that are standing perfectly still. This is the world of statics.
The syllabus breaks it down into two separate parts, which is super smart. On one side, you've got static electric fields. These come from stationary charges, and they're governed by Coulomb's law, which is basically the fancy way of saying opposites attract. Then on the other side, you've got static magnetic fields. These come from steady, unchanging currents, and they're described by Biot-Savart's law. That just explains the magnetic field you'd find around a simple wire with current in it. So for now, think of them as two totally separate, quiet forces.
And that's really the starting point. An engineer has to master these two static pillars completely on their own first. It's kind of like learning your letters and your numbers before you can even think about writing sentences. This is the absolute non-negotiable first step.
All right, now things get really interesting, because this is where everything changes. What happens when those quiet, unmoving fields suddenly start to, well, move? This is the moment where the two separate ideas, electricity and magnetism, they fuse together into something totally new and incredibly powerful.
And this is the moment of pure genius, captured right here. Faraday's law shows us that a changing magnetic field actually creates an electric field. But then comes the big breakthrough from Maxwell. He realized the reverse is also true. A changing electric field creates a magnetic field. So they create each other, back and forth in this perpetual dance. It's a chain reaction that doesn't need anything else to keep going.
And that self-sustaining chain reaction, that's it. That is an electromagnetic wave. This is the fundamental origin of, well, everything. From the light you can see to the Wi-Fi signal you can't, it's all just this incredibly elegant dance between two fields. This whole beautiful concept is wrapped up in just four elegant equations. We call them Maxwell's equations. And they are, without exaggeration, the mathematical bedrock for all modern communication technology. If you master these, like the syllabus demands, you can understand and create pretty much any kind of wireless signal. Okay, so Maxwell's equations give us the power to create and understand these waves. Fantastic. But just making a wave isn't enough, right? You need to control it. You have to send it from point A to point B reliably. So the next big engineering challenge is, how do you build highways for these signals? And this brings us to the last major part of the syllabus, transmission lines. Think of a coaxial cable hooking up your TV, or even the tiny little copper traces on a circuit board. These are specialized structures, highways really, designed to guide those electromagnetic waves exactly where they need to go, keeping the signal contained and focused. But, of course, there's a problem. What happens when your signal highway reaches its destination, let's say an antenna or some other component? If that connection isn't perfect, the signal can literally bounce back, kind of like a wave hitting a solid wall. And for an engineer, that is a huge, huge issue. And the solution, a key skill taught in this course, is something called impedance matching. It's basically the art of making the destination look like a wide open road to the signal. That way, all its energy gets absorbed perfectly instead of reflecting back. I mean, getting this right is the difference between a crystal clear signal and just a bunch of useless static. It's what makes high-speed electronics actually work.
So let's zoom out for a second and look at the whole picture. We've basically followed the breadcrumbs laid out in this one syllabus, all the way from these foundational laws to the complex tech that's probably sitting in your hand right now. And as you can see, the whole thing is a perfect logical story. You start with the static rules to understand the boundaries. Then you unify those rules to create waves and figure out how they travel. And finally, you learn to guide those waves down transmission lines by designing things like impedance matching. It all just fits. So you see, a syllabus like this, it's not just some boring checklist of topics. It's a narrative. It tells the story of how we took these fundamental laws of physics and, step by step, built the entire framework for modern wireless communication.
And that really just leaves us with one final thought. This academic document, it's the blueprint that has built our connected world up to this very point. So the real question is, for the next generation of engineers learning from this exact blueprint, what are they going to build next?